All right, so hello once again. And this time it's going to be a question regarding boiling and melting points. And essentially, especially within this chapter, boiling and melting points are going to depend a lot upon molecular structure and upon the polarity and forces that act between the molecules, or what is known as intermolecular force. Let's take the example of NCl3. Now, NCl3 is composed of nitrogen and 3 chlorines, and N has 2 electrons at its top out of 5. It has 5 electrons total, and it's bonded covalently to 3 chlorines, which donate one of its own electrons to form each pair. So the structure ends up being pyramidal with a tetrahedral electron domain and a pyramidal geometric structure, which means its bond angles are going to be 107 degrees. Now, looking at this molecule, there is apparently going to be not any hydrogen bonding, because hydrogen bonding requires the attachment between a hydrogen and one of the very electronegative and small elements of nitrogen, oxygen, or fluoride. In this sense, the absence of hydrogen bonds means that this molecule is not going to have them, and thus that intermolecular force will not be present. The next intermolecular force is known as dipole-dipole, the next strongest, of course. Dipole-dipole forces are essentially permanent charges upon atoms that occur due to electronegativity differences. And, well, what does that mean? Essentially, if we take a compound like HCl, we can see that hydrogen's 2 in electronegative value, and Cl is about, I think, 3.98, about 4. So the electronegative difference ends up being about 1.9, somewhere around that. Not enough to be ionic, but a very, very polar compound. And what this ends up doing is the electrons end up spending little time around the hydrogen and far more time around the chlorine. And electrons, by their nature, are negative. And the more place they spend in somewhere, the more negative the area becomes, represented by negative delta. That would be this area. Conversely, the hydrogen side becomes positive delta, as the electrons spend less time around them. To me, I like to think of it as a sort of tire, like one of those big tanks, if you've seen them before. They have big wheels that spin with a tiny wheel in the front. And if you look at the tread, a particle, in this case the electron, the tread will go much faster on the tiny part and will take a much longer time around the big part. In this sense, a negative charge is created because the electron spends more time around it. This is known as a dipole-dipole charge, and this is what NCl has. And the reason for this is because all of the electrons, the negative forces from the chlorine, due to their electronegativity, have a method to circle the atom and make this area slightly negative due to the outlet of an unbalanced electron pair. And whenever you see structures, if there's ever an electron pair upon an element, it's always going to go out that way, and that side will always be negative. So this molecule is going to end up permanently polar and is going to be, as a result, influenced by dipole-dipole forces. It's also going to have London dispersion, and London dispersion is kind of difficult. London dispersion is temporary, and it doesn't occur for very polarized molecules. It doesn't have that much of an impact. It only really works when molecules get super massive, like, for instance, hydrocarbon chains, which have hydrogens and carbons attached to them and are nonpolar because everything cancels out. Their electronegative charge has nowhere to go. But they can still temporarily, because the electron cloud can at any moment disappear or reappear around in a sort of strange configuration, have temporary shifts in electronegativity that can cause some movement and some stick together. And the more electrons you have, the more London dispersion there is. And now you might be thinking, well, what the heck, Glenn? What does this have to do with melting point? Well, melting point and boiling point is dictated by intermolecular forces. And the evident aspect of this is that the more polar something is, we can take HCl as an example, a dipole force, the more this negative side is going to want to connect with similar molecules to it. For instance, attracting to the positive side, so you end up getting a lattice of HCl, ClH, where their negative and positive sides tend to aggregate more. And this results in a dense, more liquidous substance. This is also the principle that allows water to be liquid at the room temperature it has, because its oxygen molecule has 4 electrons in a tetrahedral electron domain, but a bent molecular geometry, with 2 hydrogens that end up being positive as a result of being small and having a hydrogen bond, remember. And as a result, these negative area around the oxygen, due to the electrons being able to vent out that electronegativity, attract to the positive H's of other water molecules. As a result, water has a very high boiling point, and it cannot be vaporized very easily. And essentially, when incurring a boiling point, you want to first look at if it has a hydrogen bond. If there's a hydrogen bond, it's always going to be the high boiling point. And remember, a hydrogen bond is going to be if you have a hydrogen atom attached to nitrogen or oxygen or fluorine that is directly touched and that is asymmetrical. Water would be a good example. This is asymmetrical, it bonds. Likewise with HF, hydrofluorine, which bonds to itself in this fashion and so has a very high melting point.